Hello students, welcome to the 31st lecture on particle physics. And in the last lecture we were discussing about the interstellar matter and the formation of stars. Today I shall continue from there. What we had discussed, that the space between the stars, they are not empty, they are filled with gas and dust particles and they are nothing but atoms. Therefore, we have atoms in between the two stars throughout the universe that we talk about. The density of interstellar matter is million times less than the density of vacuum that we create in our labs using the most efficient vacuum pumps. The interstellar matter consists of gas and dust. The density of interstellar gas is about 10 power minus 24 gram per centimeter cube, and remember the air density, which is around 10 power minus 3 gram per centimeter cube, and density of water, that is 1 gram per centimeter cube. Therefore, you can think of how small the density is, and that is why we are unable to see when we look at the sky. And this is what I have shown here. The density of air, though it is 10 power minus 3 gram per centimeter cube, we are unable to feel it. And when we talk about 10 power minus 24 gram per centimeter cube, that is really extremely small. Now, I am talking about gas and dust. The density of gas is 10 power minus 24 gram per centimeter cube, and dust is further smaller than that, and that is around 10 power minus 26 gram per centimeter cube. That means 100 times smaller than the density of gas. Now, the important question is, what are these gas and dust? The answer to that is, they are nothing but mainly hydrogen atoms, some percent of helium atom, and less than a percent of heavier atoms. 63% of the total galactic mass belongs to the stars, while the rest 37% is present in the form of interstellar matter. Modern observation of the interstellar matters indicates that it consists of 71% hydrogen, 27% helium, and 2% heavier elements by mass. While in terms of number of atoms that you talk about, 92% of hydrogen atoms, 8% of helium atoms, and less than a percent of heavier atoms. That is what our this interstellar matter consists of. Now, the other point which I talked about was about nebula. What I had told you, that these are the dense cloud of atoms, or say interstellar gas and dust particles. That means this distribution of interstellar matter is not uniform. There are places where the density is large, and this is known as nebula. These nebula can be behind this nebula you can have a bright star, and then you have a different stars behind them, and you can talk about bright nebula, you can talk about hydrogen nebula, where you have the chief dominance of hydrogen atoms. More than 95% you have hydrogen atoms in neutral hydrogen nebula. So the stars form within particularly cold, dense and massive regions known as giant molecular clouds or nebulae. The nebulae are usually found in the galactic plane. The density of these clouds is significantly higher than the interstellar matter, and this vary between 10 power minus 9 gram per centimeter cube to 10 power minus 23 gram per centimeter cube. Remember, I told you that the density of cloud gas is 10 power minus 24 gram per centimeter cube, and dust is 10 power minus 26 gram per centimeter cube, while there are regions where the density is almost say million times more than the density, average density of interstellar matter, and these are the places which we are calling it as nebulae. The temperature of these clouds vary between 10 to 30 Kelvin. In terms of the masses of these giant molecular clouds, this vary from 10 to the power 4 to million times the mass of the sun. Here M circle with a dot represents the mass of the sun, and remember the mass of the sun is typically of the order of 10 power 30 kilogram. Therefore, you can see that how massive these gas and dust particles are when you just, here you are talking about a nebula, typical nebula. These nebula are classified into three types: bright nebula, dark nebulae, and neutral hydrogen nebulae. Bright nebulae exist, and if there are bright stars behind that, then the temperature is sufficient to excite the atoms in these nebulae, and therefore the radiation is triggered by nearby stars and they look bright. For example, in some bright nebula, we observe some dark round cloud. Those are called globules. Therefore, we have stars and then we have interstellar matter, and in this interstellar matter there is a small place where the density is large, that we are calling it as nebulae. And then if there is a bright star behind this, the temperature of this star is sufficient enough to excite the atoms in these nebulae, and that is why you are seeing it bright. And then in this spot there is a place where the density is larger than the average density of the nebula. Therefore, we are talking about three things here: the average density of interstellar matter, the average density of nebulae, and then the place where the density is larger than the average density of the nebula. Therefore, these globules are believed to be the progenitors of stars. The Eagle Nebula is rich in dark globules, which are the first stage of star formation. Therefore, since the density is large, therefore you are seeing it to be dark. Now, how a star gets formed, that is what we have talked about in the last lecture, and I gave you the example, one example, that during the formation of a star releases a huge amount of matter, and that travels in space, and that creates may trigger the formation of a star. But similarly, during the death phase of a star supernova explosion, the star releases a huge amount of matter, that gets released in the space, and that may trigger the formation of a star. And the third is intergalactic shock waves. Those travel in space. We don't know the reason from where these intergalactic waves are coming, but these intergalactic waves are also thought to be the progenitors of stars. Because of that, you can have the formation of stars. Now, these tremendous shock waves that move around the entire galaxy, these waves are known as intergalactic waves, and their source is not yet known. Very massive stars during the formation undergo a period during which they release enormous quantity of matter at great speeds. These supersonic bursts cause pressure waves. They can be the cause of the formation of stars. Now, when a massive star exhausts its thermonuclear fuel, it can explode and eject shock wave that expands at the rate of 10,000 kilometers per second, and these shock waves travel in space, they pass through these globules, and when they pass through, they disturb the area around it. Now there is a gas pressure because the density of air molecules in these globules in this area is large. Because of that gas pressure, one thing may happen: either they fight back these shock waves, or if the shock wave dominates, then density in some area of this globule further becomes very large, larger than the average density of the globule, and that is what we shall talk about later in this lecture. So therefore, what I am talking about, that we have globules, and see inside that we have the uniform distribution of atoms. Now if there is a shock waves, therefore this shock wave, when it will travel, it will disturb the texture. Now if the pressure wave is sufficient enough to fight back this shock wave, then after some time these atoms will come back to its place. But if the shock waves dominate, then it is something like an outside army which is attacking a castle, and if the army inside the castle, they are able to fight with these fellows, then these fellows will fled away and they will come back to their normal routine. But if these fellows, these attackers, they are able to dominate, then they are going to put their mark over this castle. And that is what happens, that if the pressure waves is sufficient enough to fight back these shock waves, then after some time it comes back to its original position. However, if the shock wave dominates, then there is some area where you will have more atoms relative to the average distribution of atoms in that globule. And that means if the density at this place is becoming large, then what it will do, slowly it will attract the other atoms because of the gravitational pull, and these atoms will, as they will move closer to this part, their kinetic energy will increase, and when it will come to this place and strike this part, they will impart their kinetic energy to this system of atoms which are there where the density is large, and their kinetic energy will be transformed in form of the thermal energy. Therefore, slowly the temperature of this part which has got dense because of the shock waves, that will start gradually increasing, and because more atoms are coming towards it, therefore gradually it is becoming more massive and then more massive and so on, and temperature of this is also increasing. Therefore it is the atoms are coming towards it, it is contracting, and its temperature is gradually increasing. Therefore this is what we are talking about, that when shock waves are coming, this will disperse matter if the gas pressure fights back. Then after some time equilibrium will come back. If the shock wave dominates, then the density at some point will become larger, and the cloud will start attracting surrounding matter, and because of the rise in temperature, you will have slowly you will have a stage when the nuclear fusion will start taking place. Therefore, first gas pressure attempting to expand the cloud, while the cloud spins more rapidly as it collapses because of the conservation of angular momentum. So therefore, when this matter is collapsing and getting confined to some place, a stage is reached when the temperature is sufficient enough to start the nuclear fusion reaction. Therefore, now when the nuclear fusion reaction starts, Now the radiations will come out. Now at the same time, the atoms are also falling. Therefore, there is gravitational collapse, as well as there is a radiation which is coming out from inside, and then there will be an equilibrium. And when this equilibrium is reached, that is the point when we say that a star has come into the main sequence. Therefore, a stable star is the one where the gas pressure, there is an equilibrium between the gas pressure and radiation pressure. Therefore, there is a compromise between fusion energy and the gravitational energy. There is a balance between that. Now, as long as thermal energy and heat can be radiated away, the protostar stays cool and pressure remains too weak to slow the gravitational collapse. As the shrinking cloud becomes smaller and denser, some of the thermal energy cannot escape and is trapped inside the collapsing cloud. The internal temperature and pressure will rise, which raises the opacity of the gas. When the contracting gas becomes opaque to its own radiation, it has reached the status of stellar embryo. The photosphere defines the boundary between the inside and outside of the star. Eventually, the core temperature becomes high enough to ignite the thermonuclear reactions, and the protostar becomes a star and takes its place in the main sequence of the Hertzsprung-Russell diagram and completely halt the collapse. Therefore, this is the point where the star reaches to the main sequence, nuclear fusion has started, there is no further collapse, there is stability. Okay? And this is what we have discussed it on the last turn, that this Hertzsprung-Russell diagram is basically, this shows the spectral classification of these stars. It shows how much a star is luminous. It shows that all these stars are not of the same type as we have discussed on the last turn. You have O, B, A, F, G, K, M, R, and these types of spectral classifications have been done, and our sun is a G2 type star that we have discussed, because there is sub classification between O to B, B to A, and that is O, A1, A2, A3, A9, G1, G2, G3, G9, and so on. And our sun is a G2 type star, where the surface temperature of the sun is around 6000 degree Kelvin. And this, our sun, is not a bright star. As you can see that there are stars where surface temperature is 50,000 degree Kelvin, while there are also stars like R and N which have not been shown here. Their surface temperature are around 3000 degree Kelvin or 2500 degree Kelvin. Therefore, here we have shown that on this axis, if you look on the y-axis on the right hand side of this diagram, you can see that sun, if we represent the luminosity of the sun to be 1, as we know that the luminosity is around 10 power 24 watt, this luminosity is, if 1, there are stars which are million times more brighter than our sun, and as well as there are stars which are more than 1000 times less brighter than our sun. And that is what I am calling it when I am telling you that there are stars which are 1000 times, 10,000 times, million times brighter than our sun. That means our sun is not among the brightest stars in the universe. Now, the important point is what we have talked about. To summarize, a protostar assembles from a collapsing cloud. Then the protostar shrinks and heats as the gravitational energy is converted into the thermal energy. Then surface temperature rises when the radiation dominates. And then finally, in the fourth step, the fusion rate increases until it balances the energy radiated from the star surface. And this is what we are talking about, a stable star. Now, when we talk about brighter stars or the stars which are much bigger and much larger in luminosity, the infalling particles of massive stars experience much greater gravitational force than the particles of low mass stars, and they reach the main sequence more faster. That means, if for example, if our sun from protostar to main sequence, if it has taken millions of years, then the other brighter stars, they might have taken 10 power 4 years, they might have taken 10 power 5 years. Therefore, they have come faster than the sun to the main sequence. Similarly, when we talk about the M-type star, where the surface temperature is around 3500 degree Kelvin, which are less in luminosity in comparison to the sun, it remains protostar for billions of years. The sun with more mass spent almost say 30 million years in this phase, but the most massive stars remain protostar for only tens of thousands of years. Therefore, the lifetime of a star depends upon its mass, with more massive star living for a shorter duration of time. Now, what is a star? How do you define it? A star can be defined as a body that satisfies two conditions. It is bound by self-gravity, and that is why the shape of our star must be spherical. It radiates energy supplied by an internal source, and that is where we are talking about nuclear fusion is taking place. Now, the protostar with masses less than 0.08 mass of the sun, that means their masses are only or less than 8% of the sun's mass. They don't have enough internal pressure to ignite hydrogen fusion. That means nuclear fusion reaction there does not take place, and that means it's not necessary that in all these stars nuclear fusion would take place. If they are very low mass prototype stars, then the temperature is rising, but the matter is not sufficient enough, because you can say, in other words, when the gravitational collapse is happening, the temperature is rising, but since the matter is not sufficient enough, it is not massive enough, there will never be a time when nuclear fusion will start taking place. And eventually what will happen is radiation will come out, and slowly it will become cooler and cooler. Such type of stars are known as brown dwarfs. Therefore, they have not come to the main sequence, because main sequence means nuclear fusion reaction has started, but here the mass was not sufficient enough to start the nuclear fusion reaction. Now, when the center of collapsing star, whose masses are more than the 8% of the mass of the sun, becomes hot and dense enough, hydrogen fusion begins. Gravitation serves as the energy source for the protostars, heating them and causing the emission of radiation. But the fusion of hydrogen into helium serves as the energy source for the main sequence stars. Therefore, when the star is in main sequence, hydrogen is getting exhausted, hydrogen fusion is taking place, and that hydrogen fusion is giving us helium. For the low mass stars, the fusion of hydrogen to helium is dominated by the pp chains that we have talked about in the earlier class. But for the heavier mass stars, the fusion of hydrogen is dominated by CNO cycle. Therefore, there are two chains. One is pp cycle that we have also talked about, and another is CNO cycle. Therefore, when we talk about PP cycle, we have seen that we have neutrinos coming out in this. We have neutrinos coming from proton-proton bonding. Then from helium bonding, when this is taking place, we have the formation of beryllium, lithium. When we have the electron captured by the beryllium nuclei, we have neutrinos. When helium-3 is fusing with proton, we have 4 helium. Besides that, we are getting neutrinos. Therefore, these are the places where when we talk about proton-proton bonding is taking place, this is the place where we are also getting at the same time neutrinos. In general, in our earlier class, we saw that 4 protons in general are bonding to give us helium nucleus plus 2 positrons, 2 neutrinos and about 27 MeV of energy. But what I am telling you that this is not all the time a one-step process. Then what I am talking about is that in heavier stars, this hydrogen bonding that we talk about takes place via CNO cycle. But at the same time, whatever we talk about, what it can be realized that always there will be emission of neutrinos, and if there are no neutrinos, then that means we are not talking about fusion reaction going on inside the core of a star. Now, in a main sequence star, hydrogen in the core of a star is continuously or continually being converted to helium as the nuclear reaction occurs. This we have seen that our sun's lifetime is 9 billion years and it's going on since the last 4.5 billion years, and it will continue for the other 4.5 billion years. Therefore, our sun is going to be in the main sequence for about 9 billion years, and that means we are talking about hydrogen bonding will keep on taking place inside the core of our sun. And we have also seen that what's the rate of this burning by looking at the luminosity of sun and how much energy we are getting from 4 protons bonding. Okay. Now this, in a main sequence star, hydrogen to the core of the star is continually being converted to helium as the nuclear reaction occurs. This causes the number of particles in the core to gradually decrease, and this results in core shrinking slightly. As this occurs, both the increase in the rate of fusion and the conversion of gravitational energy into heat come into play, raising the core's temperature and making the star more luminous. The sun will continue hydrogen bonding for about 9 or 10 billion years. Now, we are talking about stars whose masses are in between 8% of the mass of the sun and 40% of the mass of the sun. They will die as a black dwarf. What is a black dwarf star? Now, after hydrogen bonding, the star will contract because again the temperature inside that is not sufficient enough to fight back the gravitational collapse because hydrogen has exhausted and you need fresh fuel. Therefore, you don't have the radiation pressure to balance the gravitational pressure, and therefore the core of the star has started shrinking, and as it has started shrinking, its temperature is going to increase. Now, if the mass of the star is less than 40% of the mass of the sun, now this matter is not sufficient enough to have helium fusion reaction. Therefore, you won't have helium fusion reactions in stars which are having masses less than 40% of the mass of the sun. Though you had hydrogen fusion reaction, but you won't have helium fusion reaction. Therefore, what will happen? Slowly again from here, like in the case of brown dwarf, there was no hydrogen fusion. Here there is no helium fusion. Therefore, radiations will slowly come out from the core and the luminosity will decrease, and ultimately such type of stars, they will become black dwarf. And in such type of stars, what happens? Instead of the energy coming out through radiation process, the energy here is through convection, and all the energy gets, all the fuel gets exhausted at the same time, and you don't have sufficient temperature for the next fusion reaction. Therefore, now we are going to talk about stars which are like our sun, or which are more massive, like they have mass of the core between 1.4 mass of the sun and 3 mass of the sun, as well as the stars which are having masses more than 3 mass of the sun. Now again here, like we have brown dwarf, we have black dwarf. Now we will talk about white dwarf stars, neutron stars, and in very brief about the black holes. Therefore, the important point is, now we have to notice that we are going to talk about first those stars whose masses are more than 0.4 times mass of the sun, but less than 1.4 times mass of the sun. Therefore, I am talking about all those stars. I should write like this, something like this. All those stars core whose masses are more than 0.4 times the mass of the sun and less than 1.4 mass of the sun. The core's mass that I am talking about, this they will die as a white dwarf, while if the core mass is more than 1.4 mass of the sun but less than 3 mass of the sun, they will die as a neutron star. And then stars having mass more than 3 times mass of the sun, they will die as a black hole. Therefore, we have brown dwarf, you have black dwarf, you have white dwarf, you have neutron stars, and you have black holes. As we have seen that we have trillions of stars, but all these stars are not of the same type. Depending upon the luminosity, we have the classification, and then we saw that we have O, B, A, F, G, K, M, R, N, etc., and they are representing the surface temperature of the star. And what I have told you, that the sun's surface temperature is 6000 degree Kelvin. Now we shall start from here. Now remember, in our main sequence, hydrogen fusion was going on, like inside the core of the sun, and this life span of this is 9 billion years. Now what is going to happen after 9 billion years? Now that is what we are going to talk about, that stars having mass more than 0.4 mass of the sun, they become red giants. During hydrogen burning, the fusion energy kept the core from collapse. That had stopped, the radiation was sufficient enough to fight the infalling matter, gravitational, the matter which were falling because of the gravitational pull, that the gas pressure from inside, the radiation pressure was fighting it, and there was a compromise and there was an envelope. Now here what happened when you won't have hydrogen burning? Now lacking a source of energy to fight gravitational collapse, the core starts to shrink dramatically. As in the case of the protostar, the contraction converts again the gravitational energy into heat and radiation. The resulting increase of radiation from the core causes the shell of the material around the core to heat up enough that hydrogen fusion begins. Remember, I am talking about this part where the core is falling, and because of gravitational collapse, further you have the infalling matter. Now, when you are talking about infalling matter, then there is an important catch that all the hydrogen in the stars have not exhausted. You have used only those hydrogens which are there in the core where the nuclear fusion was taking place. But the other hydrogen atoms, because when they have started coming closer to this core, the temperature of the core is rising. Now the outside of that core is hot enough to start the nuclear fusion reaction. That is what we are talking about. These two sources of energy, gravitational energy in the core and fusion energy around the core in the star center, result in a great increase in radiation from the center and forces the outer portion of the star to expand. Therefore, this is what we are talking about. The core is shrinking, and then you have the hydrogen around it which has started burning, and because more radiations are coming out, therefore you have a bigger star, and that is known as the red giant star. Therefore, as the outer portion of the star expands, it cools and the star moves to the right and upward on the HR diagram. Therefore, when our sun will become a red giant star, it will cover almost Earth and there will be no life. And that is why we always talk about the age of the sun to be 9 billion years. It is not that sun will not be there, or rather I should say that star will not be there. It will be there, but it will become a red giant star and the life will not be there on this planet. Now what happens when the core is shrinking? Then a time comes in million years, then the temperature is hot enough to start helium fusion reaction. And therefore, in our sun, this helium fusion has started happening, and this helium fusion is giving rise to carbon nuclei, and the radiations are coming out. But what will happen once we have exhausted all the helium? Then again there will be instability. The radiation pressure is not strong enough to fight the gravitational collapse. Now what is required? Either the carbon fusion reaction or say oxygen fusion reaction. Now in the stars which are like sun or which have got masses less than 1.4 mass of the sun, the temperature will never rise to execute carbon fusion reaction or oxygen fusion reaction, because to have carbon fusion reaction, remember from Coulomb's law which we have discussed on the last turn, 1 by 4 pi epsilon naught q1 q2 by r, this you need to overcome the Coulomb barrier, and with more protons it is what is required is a very high temperature, but the mass is not sufficient in the vicinity when gravitational collapse is happening that it will rise to a point where carbon fusion or oxygen fusion will take place. Therefore, the stars which are having core mass to be less than 1.4 mass of the sun, they will die as a white dwarf. In this stage, the core of the star has layers somewhat like onion, with a carbon core surrounded by helium shell, which in turn is surrounded by hydrogen shell. A red giant's life using helium as a fuel is only about 10 to 20% of its main sequence life. That is what we are talking about, 8 to 10 billion years. When the red giant runs low on helium, the core again shrinks and heats up due to gravitational energy, which causes the star to become unstable. The star becomes even brighter, and is known as red supergiant. Helium fusion result in carbon building up in the core, but the core does not become hot enough to allow the fusion of carbon into more massive elements. The core begins to shrink again and heats up quickly. The energy released by this heating causes the outer portion of the star to be blown outwards at a speed of say 20 to 30 kilometers per second. Therefore, when core was shrinking, radiations were coming out, and as I have told you, this because of gravitational instability, this shrinking will happen very fast, and when the shrinking will happen very fast, the radiation will come out faster, and that will have a great speed, and that will blow up, or that will expand that envelope to a great length. So therefore, the energy released by this heating causes the outer portion of the star to be blown outwards at a speed of 20 to 30 kilometers per second. Although since there is no fresh fuel, these materials cools down, and the core left behind is extremely hot, and the temperature is around 100,000 degree Kelvin. But what will happen? Slowly and slowly and slowly, those radiations will come out, and the stars will be, and that star will become further cooler and cooler, and therefore that white dwarf also will become slowly and slowly and slowly a black dwarf. Therefore, an object at a very high temperature, as we know, emits large amount of ultraviolet radiation. The ultraviolet radiation emitted by the hot core of the star causes the escaping part of the former red giant to glow as it blows away. Such a glowing object is known as planetary nebulae. Therefore, you see the outer envelope of the star, which has gone to a further distance. Here, at the core, the temperature is very hot, and therefore the point is these surrounding materials are receiving lots of energy, and they are really hot. Therefore, this region of surrounding material, which is looking brighter, that is known by the name planetary nebula. And it is not a planet, it is not a nebula. Just you may say that this name is a misnomer, because this is nothing but the outer envelope of a star, which has expanded, red supergiant. This has expanded and is getting these radiations from the parent's core, and you can say that these are now the daughter part, and they are receiving the radiations energy from the original core with which they were associated with, and they are looking brighter. The expelled material will continue to disperse because radiations are coming, and those are imparting kinetic energy to these atoms. Therefore, they will further expand, leaving behind a hot and bright core of carbon and oxygen. The core remains at its very luminous stage for a relatively short time, quickly moving down the HR diagram to become a white dwarf. And then I am telling you that white dwarf also, the radiations will come out, and ultimately that will also become a black dwarf. Therefore, what I am talking about, you see these bright places. Here we are talking about that these are associated with, they were part of the star, but because of this radiations coming out, it has expelled the material outside of the envelope of the star, and the radiations falling on this material, making them brighter, and they are called planetary nebula. Therefore, we have a white dwarf core and then a planetary nebula. But again, I am reminding it to you that it is not a planet, neither it is a nebula. It's a remnant of a star. Let us stop here, and in our next lecture, we are going to start from this place. Thank you very much.